Hi everyone, my name is Bazaliy, and today we'll talk about jailbreaking Apple Watch. Okay, let me fix it. Oh, yeah, should be better. So, once again, yeah, I'm Bazaliy, and I'll talk about jailbreaking Apple Watch. I work as security researcher at Lookout when I focus it on malware detection. Last year I was a lead researcher on a Pegasus exploit chain, and currently focus on advanced exploitation techniques for software, hardware. I co-founded Fried Apple team, and I'm after of various jailbreaks for iOS, tvOS, and now for watchOS. So what is Apple Watch? It is a smartwatch device that was released in 2015, and it uses Apple S1 or S2 processor. It's basically a 32-bit architecture processor called the ARM7K, which is derived from ARM7A. It uses a duplicate engine for user notifications. It has a 512 megabytes of RAM, and it's running the watchOS, which is derived from iOS. So I hear a question a few times: why we even need to jailbreak a watch? Well, I have a few watches at home, and I thought it should be pretty interesting from a security researcher point of view. Why not give it a try? Why not try to jailbreak it? Because if I can jailbreak it, I have access to file system, so I can check the watchOS internals. And it should be just fun to run debuggers like Radar or Frida on this teeny Apple Watch screen. Or use it as iPhone attack vector to send some malformed data to the iPhone. So before jumping to jailbreak internals, let's make a quick overview of the Apple Watch security, which starts from a secure boot chain where each element in the boot chain is checked to be properly signed by Apple, and it basically stops boot if it's not. The next thing is mandatory code signing, so all code that is running on the watchOS should be signed by a trusted party. The sandbox, which is limiting application access to other applications' data and limiting application access to critical system APIs. Exploit mitigations like address space layout randomization on user mode and the kernel mode, heap and stack cookies, and of course the data execution prevention. Starting from second generation of Apple Watch, there is a hardware-baked secure enclave processor that's used for safe crypto operations. And the data protection. So all user data is encrypted when device is locked. So after thinking about the possible attack vectors on a watch, and the first idea was, why not try to send some malformed payload or even fuzz USB descriptors? Because there is a teeny port, the debug port on a watch. If we detach some of these things, we see this small port. The problem here, the cables from this debug port to USB, they are not public. So I don't want to mess with all the non-public hardware, so I decided to switch for other way. The other way will be send the malformed emails or messages or photos from a phone to a watch and try to basically attack the parser. Well, this will be still limited by a sandbox, the parsers. So I need additional out of sandbox bug to continue the jailbreak. Well, starting from watchOS 2, Apple added the support for user-defined application extensions, which is basically the native code that's running on a watchOS. So I decided to stay on this one. It looks pretty good, and I have a freedom on a bug choice. So to choose one of the unfixed bugs and use it for a jailbreak. So this is how the jailbreak may look like. So first of all, we need to allocate a kernel in memory. All the security measurements are in a kernel, so we need to patch a kernel to disable them. For this one, we need to break a KSLR and find the kernel base, then read the whole kernel to user mode, start analyzing it, look for gadgets, set up primitives like read-write, then finally patch a kernel to disable the security restrictions, and run the SSH client on a watch. Well, looks doable. So, as I say, I have a few versions of watchOS at home, like watchOS 2 and watchOS 3, and I start looking for good bugs. For watchOS 2, there is a pretty good bug, the CVE4656, which is user-free in a kernel. And this bug is famous because it's a part of the Pegasus exploit chain. So this may be a pretty good candidate. As alternative way, it's CV4669, which is a MAC port register. It can be exploited on 32 bits as a free in a run zone. But I decided to stay with OS and serialize because it's more stable. As for watchOS 3, there are two bugs, CV7644, set DP control, which was discovered and exploited by Ian Beer in a Mac Portal jailbreak, and CV2370, which is heap overflow in voucher extract recipe. It was used later by Luca Tedesco in YALO 10.2. So I decided to stay with CV2370 for watchOS 3. Okay, we now know the bugs, how to get the kernel level code execution. Let's start from looking at kernel base. There are a few good CVEs, CVs 4655 and CV4680. They both share the same problem. So because during the parsing in a kernel, one of the objects, which is like OS number object, it's basically object constructor missing the bound checking, which leads that attacker can create OS number with a high number of bits. And later on, this high number of bits will be used as an object len. And the object len will be used to copy how many bytes we need to copy from a kernel stack to a kernel heap and return to user len. So that leads that kernel stack memory will be leaked and we can determine a kernel base. And this bug can be triggered from a sandbox. I will check more detailed. So the bug is in iOS unserialized binary, which is a method to handle binary serialized data. It converts the binary format to a basic kernel data objects like arrays, strings, booleans, numbers, and so on. And the problem is when the parser goes to OS number. The OS number represents the number object in a kernel. And it basically blindly trusts the input arguments, here the value and len, and just call the designated constructor, which is OS number init. And here is a problem, because one of the arguments, which is new number of bits, is set to one of the class variables size. And this size will be used later on other method OS number of bytes. It leads that a return value of number of bytes is fully controlled by attacker. And why it's bad? Well, later on in IO registry entry get property bytes, this number of bytes method will be used to calculate the OS number length. And which is bad because OS number value is stored on a kernel stack. Here it is offset bytes buffer. And basically the object length will be used to copy that many bytes from a kernel stack that needed from this buffer and return to user mode. As we control how many bytes will be copied, we can control, well, like 255 bytes and basically leak some of the kernel memory. If this kernel memory will have any of the kernel pointers, it will be enough to determine the kernel base. So we know the kernel base, now it's time to get some code execution in the kernel end. So CV4656 is pretty good. It's user-free in the same iOS unserialized binary, but in the different branch. The problem here that during the serialization, the OS string object will be deallocated, but the pointer to object still stored in one of the arrays. And later on, the retain method will be called on this deallocated data, which lead to user-free. So if we can relocate this object with attacker control object, like fake OS string, which point to attacker control vtable, we can get the kernel mode code execution. This is how it looks like. So the same iOS unserialized binary, which parses the binary encoded values and return the iOS objects. It's the problem in when the objects will be deserialized and save it to objects array. So now we see the setAtIndex macro that basically stores the pointer of an object, but not doing any memory measurement on it, like not retaining the object. This is bad because later on, when OS string will be casted to OS symbol, the OS string object will be deallocated, but the pointer to it is still exists in one of the arrays. And in a case of KIO serialized object, which is a reference to an object, it will be retained, which causes the use of the free. So we get the kernel level mode execution, and the problem that we need to know what to execute in a kernel. So basically, there are no watchOS dump available in public in that time. As well, there is no keys for watchOS kernels. So, and to continue jailbreak, I need to know some part of a kernel. And I have an idea. Why not create the fake OS string, point it to the beginning of the kernel, and basically read the kernel as an OS string chunk? Looks doable. The problem here is that even the object is fake, we still need the real vtable offset. And the vtable offset is stored in a data const, which means basically I need some parts of the kernel to dump a kernel. It's like a chicken and egg problem. And I start looking for ways, is there any possibility to dump this vtable just in a runtime? Well, it is. As we know, the vtable is stored in a data const in a kernel. And the data const is referenced in a kernel macro header, which means is somehow we can leak the kernel header, we can leak the data const address in a runtime. And the offset to the data const reference in a header is always constant. There are like 0x2 to 4. I determine it from similar XNU build. So if in runtime we can branch to start of the kernel plus this offset, we can leak the data const. And how we can do it? Just use it as a fake vtable pointer. So device will crash, the kernel will crash, but we will get the data const address. Now if we know the data const, I was trying to calculate the offset for vtable by checking again the similar XNU build from a start of the data const to a vtable. Unfortunately, it's not just work out of the box because the kernels are different. So I was trying to tune it with plus or minus 4 bytes delta, but in reality, it never works. So later on, I found that the difference are really significant between watchOS and the iOS. It's like more than 4 kilobytes of difference in a data segment. So this method is not working. Okay, I start looking. It should be some other way to do it. And I look at OS string layout in a memory. So for 32 bits, the size of the object is like 20 bytes. For 64 bits, like 32 bytes. And the very first pointer of an object is a pointer to object vtable, and which is more interesting, the layout of the vtable. So our bug triggered the use of the free by calling a retain. And retain is a like 5th element in array. So I start looking, well, it should be some way to like reuse this information. Here is what I mean. We have the OSString object layout in a memory, and the very first pointer of OSString object is pointed to object vtable. And the vtable is pointing somewhere in a kernel code section, and our trigger, which is iOS object retain, is like 5th element in array. Okay, so how we can use it? So what if the object that will be triggered in a bug will be deallocated but not reallocated? So this memory chunk will be marked as free, and which is more interesting, this free memory chunk will be pointing to the next free memory chunk in a free list. This is interesting. This is how it looks like. So we have a node in a free list. We have like free list head, and now each node is pointing to the next node in a free list. And again, it's like the first pointer in this free memory chunk is a pointer to the next free memory. So what if we not reallocate our string object? This memory will be marked as free, and basically now it's pointing to the next free node in a free list. And this pointer will be interpreted as OSString vtable pointer. So if we call retain on it, it will basically branch out of bounds on the next node. This is what I mean. So again, we have the nodes. Each node is pointing to other node. And if we call the user to free without reallocating an object, one of the nodes will be interpreted as OSString. And the beginning of the node is a pointer to the next node, and this pointer will be interpreted as a pointer to OSString vtable. Then we call a retain and run out of bounds, basically branch out of bounds to the next node. But what if we can control the next node? So if we spray OSString objects, make a few holes on a heap, then basically trigger use of the free. The pointer to the next node will be interpreted as a vtable, which is now branching to the next node, but if this next node is OSString, will be branched just in the beginning of the OSString object, which is a vtable. This is what I mean. This is the initial state of the heap with like, some memories allocated. And I basically heap sprayed a lot of OSString objects. So we fill memory and trigger some of those OSString deallocations. So basically now we have holes on a heap and trigger the user to free. One of these holes will be interpreted as OSString object and pointing to the next hole on a heap. And when we call the retain, it will be out of bounds for the next node, which in our case is OSString. So we will dump a vtable in a panic lock. Well, this method is working. I get it working on 64 bits. I can dump a vtables on 64-bit kernels. But for 32 bits, it's pretty painful to make it work because of the size mismatch on the zone size and the object size. So I say, oh, it should be some other way to do it. Well, I started looking for similar kernels. And I found that the reference to OSString is OSString vtable is in iOS and serialized binary. That's interesting because our bug is in iOS and serialized binary. And iOS and serialized binary is referenced in iOS serialized XML. So say, okay, if somehow we can leak one of the opcodes from iOS and serialized binary, we should like calculate this vtable offset. Excuse me. So yeah, should be doable. So I crash in iOS and serialized binary during the object deserialization. Kernel will crash, device will crash. I get a panic log. I just copy it from a watch, read the LR register. Well, and now I know where the iOS and serialized binary is like layout over the start of the kernel. Which is interesting because now we can start to dump in the opcodes via panic logs. So we can use the address we want to dump as the address of our fake vtable minus 0x10. This vtable is, this pointer will be interpreted as a vtable and branch to this address. Obviously, the device will crash, but we get the kernel panic log and the register state. And the register state will contain basically the PC register, which is pointing to the content of the address. So I start dumping a kernel by 4 bytes by crashing a device. Use an address as a fake vtable, the watch crash, wait until it's restored, and now I need to copy panic somehow. That's the problem, because it's not just work out of the box. So I need to jailbreak my phone, SSH to a phone, trigger special service, which basically copy panic from a watch to a phone, then copy it to a Mac, parse the panic, get the address content, put it in disassembler, get the opcodes, and update this address with like plus 4 bytes delta, upload it to a watch, and repeat. So it's like, you can say it's a pretty painful way to dump a kernel. I can say it's pretty fun. Yeah, so I have a lot of panics and a lot of crashes. Once again, how it look like? So we need to start dumping opcodes in iOS serialized XML until we found a branch to iOS and serialized binary. As soon as we leak this address, we can start dumping opcodes in iOS and serialized binary until we found the reference to OSString vtable. It could take like another 10 panics. Again, the full attack plan: crashing iOS and serialized XML, dump the 4 bytes, put in disassembler, read the opcode until we find the opcode which is branching to iOS and serialized binary. Leak the address and start leaking iOS and serialized binary opcodes until we found the reference to OSString vtable. Yeah, so it takes me like a long time to dump a kernel by this way, but it's doable. This is how long it takes. Usually it takes like 5 minutes to recover a watch after a panic, and it takes another 5 minutes to fetch a panic from a watch, because as I say, I need to jailbreak a phone, SSH to a phone, and like keep trying and triggering the special service that is fetching all the panics. Then copy it to my Mac, parse it, and I really don't find any way to automate the process because I need to recompile the binary all the time and re-upload it over the Bluetooth to my Apple Watch. So it takes me just 2 weeks to dump the vtable. Yeah, but now I have the vtable, now I can construct my exploit. I use the fake OS string with a real vtable, point into the beginning of the kernel, and start reading kernel as OS string chunks. We can even read them in a user mode using IO registry entry get property. So I lick the kernel header, calculate the kernel size from a header, and dump the whole kernel into user mode. Okay, we have a kernel, but there is no symbols. So the first thing I've done, I've started looking for a kernel extension, basically drivers in a kernel, which are pre-linked to this kernel. There are a few ways of doing it. We can look for the XML, which is usually at the end of the kernel. We describe all the kernel extensions that pre-link to this kernel. Or in a bad case, we can just look for a Mako header magic. And if you find a magic, we know this is the beginning of some of the kernel drivers. So I find the kernel drivers, and the next step is to find the system call table. The trick here that system call table not really changes over the watch OS version. So which means that Apple add the new syscall at the end of the table, but they not really change the syscalls in the middle of the table. So if we found the beginning of the table, we can automatically resolve like more than 400 functions and basically get the symbols. The same for Mac traps. And finally, we can resolve IO-kit object with tables and get like even more symbols. So I have the semi-symbolicated kernel, and I started to analyze it and set up the primitives. We already have the exec primitive with use after free. So all I need to find some interesting gadgets for read and write. Yeah, so they are on a slide. We set up the primitives. We get a semi-symbolicated kernel, and one thing I need is to get the internal kernel structures layout. In this case, there's a proc structure, which represents the process structure in a kernel space. And the kernels are different between iOS and watchOS, and like I cannot even use the XNU source code again because of the differences. So I start reconstructing this proc structure just in runtime by looking for proc underscore functions. They are referenced to some of the fields in the proc structure, so I can reconstruct the layout I need. In some really bad cases, I just dump the piece of memory and look for constant values. For example, like CPU type or CPU subtype. They're always constant on watchOS, and I know, okay, if it's a CPU type, it should be like a field 0x10 or so. So I semi-reconstruct a few of the structures that I need, and well, now it's time to find the patches, what to disable in the kernel. I use a pretty classic approach called the patch finder. So when we are looking for a string or byte references, find a pattern, find a reference to it, and with some additional instruction analysis, we can find the beginning of the function or the variable we need or so. Again, resolving the syscall table will be pretty useful here, as we can automatically resolve more than 400 functions. In some bad cases, RM32 instruction emulation was needed to determine where the sum of the variables are located. So it was a pretty big win for me. I get a semi-symbolicated kernel, I get an internal structures layout, I know what to patch. Now it's time to patch. So I begin my jailbreak by getting escalating to root privileges and get out of the sandbox. So the most easy way to do it is to patch the setRealID function. So there is no kernel patch protection on 32-bit kernels, including the Apple Watch. So nobody really prevents us to basically patch a kernel and patch the kernel page tables. So I patch out the checks in setRealID and just call setRealID 00 to get a root. Or there is other way if we don't want to patch the kernel code. Iterate the heap, find the pointer to the all proc pointer. In this all proc, find the pointer to the proc structure of our process. In this proc structure, find a pointer to ucred structure. And in this ucred, basically update UID, GUID, or UID fields and basically become a root. The same thing is how to get out of the sandbox. The same ucreate structure, just null out the sandbox label. No label, no sandbox restrictions. So we are out of the sandbox. The next thing is how to obtain the kernel task. The kernel task is a pretty useful way to write anywhere in the kernel memory, read anywhere, and even to allocate the kernel memory. So most obvious way to do it is to patch task for PID. It's a special API that returns the process task to a user mode based on the process ID. Of course, there is a hard-coded check if the process ID is 0, which is kernel, return null. So we can patch out this check and just read the kernel task. Other way to do it is, again, iterate a heap, look for an old proc pointer. In this old proc pointer, find the proc structure for a kernel, find the pointer to a task structure in a kernel memory, and save the send write, which is as self. Just write it to our task bootstrap port. Then in user mode, we can read it by task get special port. It will convert this pointer to useful task structure. Well, yeah, we get the kernel task port. With a kernel task, it's pretty easy now to write anywhere in the kernel memory, including the kernel text. So I start disabling the code sign checks. There is a global variable called debug, which is referenced by all PE IcanHas debugger functions, which set the debugger capabilities for a kernel or one of the drivers. So we can set it globally to 1, or we can patch PE IcanHas debugger only for a kernel extension we need by updating NL simple pointers. The next thing is update the amphi variables, like CS enforcement disable and allow invalid signatures. This will allow us to run any unsigned code on the Apple Watch. And the last thing we need is to remount the root file system. The problem here is that the root file system is mounted as read-only, which means if we want to overwrite it with some of our binaries or just add the new binaries, we need to remount it first to be writable. There are a few ways of doing it. There is a mock mount function in the kernel, and this function is checking if the file system is a root file system, prevent it from remounting. So we can patch out this check and call remount, or again iterate a heap, find the pointer to rootfs vnode. In this vnode, find the pointer to the mount flags, and basically remove a check and then remove the flag which represents this file system is a root file system. Which means this file system is not root file system. We can easily remount it with a mock mount. Additionally, we need to patch lightweight volume manager. It's a special kernel extension which is prevent us to write any data to protected partitions. In our case, the rootf is a protected partition, so we need to find map for IO function and patch out is write protected check. In addition, set PE IcanHas debugger capabilities in this lightweight volume manager. So yeah, basically we patch a kernel, we disable most of the restrictions. So now I start to compiling my payload. I recompile the drop beer, which is lightweight SSH client for this ARM7K architecture, and recompile the basic tools package like PS, chmod, ls, and so on. Put everything in my watchOS extension, and basically, as soon as I get out of sandbox, copy it to a root file system. There is a problem here. When I spawned the drop beer, it got killed. It got killed by a sandbox, which means that watchOS has more restrictions than the iOS. So some of the things that just work on iOS get killed by a sandbox on watchOS. So I just found the pointers to specific sandbox operations in a kernel and just nulled them out. Okay, now it should work, but I have a surprise. Here's the list of watchOS interfaces. The AWDL0 looks promising, which is Apple Wi-Fi Direct. But as we see, now it supports only the Bluetooth, which may be a problem because I plan to basically connect from my Mac to a watch over the SSH, and I need to somehow to figure out how to run this SSH over the Bluetooth. And there is a way. Thanks for Luca to point me to this possibility. We can use a mobile framework, a mobile device framework on a Mac and send a special message to your phone. And the fun part, that phone should not be jailbroken. It can be any release phone. So we send the message, we would say, hey, please start forwarding service port with a port 22. And we get a response, which is a companion proxy service port. So basically what we done, we bind the port on a watch to some random port on a phone. And later on, we can use this port on a phone to bind it to some port on a Mac. Oops, what happened? I guess the HDMI. Yeah, okay. So as I said, we bind some port on a watch to some random port on a phone and bind this port on a phone to some port on a Mac, and basically over this USB and Bluetooth we can run the SSH connection. And basically it works. Now I can show you how. Okay. Yes. So yeah, the very first thing I need to do is like bind this port. So I call it like a Bluetooth proxy, which bind port 22 on a watch to a phone and bind the same port from a phone to my Mac. Now I can use that just a local host with this port to connect over the Bluetooth to a watch. Yeah, we got the password prompt, and yeah, we got the shell spawned. So let's prove that we are running on the Apple Watch by running the uname, which is Apple Watch on watch 1.2. Okay. Let's try one of the command line tools like PS and dump the list of all the processes. So we see that the watch OS is pretty similar for the iOS in the point of security, in the point how the operating system work. For example, we can list our drop beer client, which is doing a SSH connection. So as I said, I recompile the basic tools like tar, like HTTP to easily archive or unarchive stuff, to copy files from a watch. But as for me, it's pretty painful to copy file from a watch then to a phone, then copy it from a phone to a Mac. So I found more easier way, just HTTP directly from a Mac to a watch and just upload the files. So in this case, I just take Proc Explorer binary. It's a tool written by Jonathan Lewin. And yeah, copy it to a watch. We get a pretty good speed over the Bluetooth. Still copying. Yeah, so it's copied. Now let's prove that it's basically on a watch by running our Proc Explorer. As I said, it's a tool, it's like similar to PS or TOP, but it shows the memory pressure and some other useful things. So the process called the watch spawn is our jailbreak. So yeah, basically the copying to a watch work. Now we need to find a way how to easily copy files from a watch to a Mac. For this purpose, I use like SSH to a watch, tar, basically archive some of the files that I need, and use a pipe to easily just dump everything to my Mac laptop. Let's check how it works. So yeah, it starts archiving the private frameworks on an Apple Watch, and I will switch to my Mac, basically to prove that we got some files copied. Yeah, as we see, like 3 megabytes of Apple Watch data was just copied to my Mac with like one single command. Okay, this is basically the SSH on a watch. So I start looking, okay, we get a jailbreak on a watch, and the watch have access to SMS, calls, even the photos and emails can be synced to a watch. It can fetch GPS location from a phone. In some cases, if you use a watch to answer a call, it has a microphone usage, and even it's involved in Apple Pay. So it may be pretty interesting to look what is on a file system. So as I said, we have a jailbreak, so it's full access to file system, and we can look for SQLite databases, not limited to the messages, the call history, contacts, emails, and so on. So what's going to be next? I basically recompiled the hooking engine that can do interposing on trampoline in to hook some of the system function, which means that I can catch data when the data will be synced between iPhone and a watch. So maybe in the future we will see the tweaks for a watch, or as I said, we can run the Frida or Radar and on this pretty small watch screen. Okay, so as we see, the WatchOS is a pretty secure operating system. Its security is equal to iOS. But still there are some differences, and some of the techniques that we use on iOS should be adapted for a WatchOS. And as for me, the data forensic may be a little bit easier on a watch as on a phone, because phones have all the kernel patch protectors and like a hardware restriction, which watch doesn't have. Okay, basically we still have a time for questions. Yeah, it was an Apple Watch jailbreak.